Hello everyone, this is Nash. Today I would like to talk about the Compton scattering effect. Different from the photoelectric effect. Photoelectric effect, we use the UV light to shine the metal, and then the electron on the surface of the metal is going to escape the metal. Okay, but for the electron, a single electron is going to absorb a complete photon to conquer the binding energy like the work function, and for the rest of the energy is going to be transferred to the kinetic energy of the scattered electron. But for Compton scattering effect is different because we are using the gamma ray. The energy of a single gamma photon is usually more than 10 electron volts. That is too high to be fully absorbed by a single electron. So it can only partially lose the energy for the electron and then scattered away. But for all this calculation, what we are going to do today, you need to have some background knowledge like the special relativity, because for the scattered electron, it will carry some the energy, usually more than 100, sometimes more than 1,000 electron volts. Carrying such high energy, your electron is going to move really fast, too fast to consider the correction of special relativity. The mass is going to enhance, and for every term that contains the mass, it should be corrected like the kinetic energy or the momentum. So let's begin. What we are talking about is a photon with really high energy and is ready to strike an electron, and the electron is at the surface of an atom. Is at the surface of an atom, and compared with the speed of light, and the velocity of the electron is relatively too slow to be ignored. And since it is at the surface of the atom, so it gets weak binding energy. So compare with the high energy photon like more than 10 electron volts, it can be regarded as free electron. So today, what you are facing, what we are dealing with, the electron can be regarded as rest compared with the speed of light, and free compared with the photon with strong energy, more than 10 electron volts. It's at the surface of the atom, so it gets weak binding. So what the electron we are dealing with can be regarded as rest and free particle, and your photon is ready to strike the electron. Your electron is going to be bombarded by the high energy photon like a gamma ray. Okay, so first, since there's no external force acting on the whole system, so the momentum is going to be conserved. So this will be our first step. There's no external force, so it will follow the conservation of momentum. So we got at the beginning we got P1 to denote it as the momentum for the incident photon. And since the electron is at rest at the very beginning, so there's no momentum, so P1 is the incident momentum is equal to P2 and plus PE. P2 means the scattered photon is going to carry less momentum and travel away. And since your electron is bombarded by such high energy photon, it will be scattered away as well and carry a momentum we call the PE. Okay, so this is the conservation of momentum. Okay, let's keep calculating this. Since the P1, rearrange it, minus P2 is equal to PE, I can square them all. Okay, like P1 square plus P2 square and minus 2 times P1 times P2 and times cosine of theta, which is equal to PE squared. This is what we got. And for this term, the P1 times P2 times cosine of theta is equal to P1 dot P2. Okay, now we got an equation number 1. Okay, ready for the second step? The second step is this world, the energy of this world is always conserved. So for the energy carried by the photon and the energy carried by the electron is always conserved. But right here, I need you to have some background knowledge like the special relativity. Even though your electron is at rest state, is not moving at all compared with the speed of light, is rest. But it does have the energy, that is the rest mass energy. And the rest mass energy is equal to, the rest mass energy is equal to rest mass times c squared. And you might be wondering, how is it possible? You are not moving at all, but you do need the energy to assemble all the molecules or atoms to assemble a complete mass. So even though a particle with mass does not move at all, it does have the energy as the rest mass energy. Okay, so the second step is the energy is conserved. So the initial energy of the system is E1, the energy of the photon, plus the rest mass energy of the electron, and which will be equal to the scattered photon and the scattered electron. And let's name the scattered photon, the energy of the scattered photon is E2 and plus E. Since your electron is now scattered, it's going to move with a really high speed because what you are bombarded with is a high energy photon. So your electron is going to move really fast. The energy of a scattered photon is usually more than 100 of electron volts. So we need to consider the special relativity, and the energy of a scattered photon is mc squared. Let me remind you, the mass is now enhanced. The mass is already enhanced. So this is the relativistic total energy. Okay. Let's just rearrange it. Let me remind you the E. In order to simplify all this calculation, I need to remind you that the E squared is equal to E naught squared plus P squared m times C squared. And this is so useful. You need to remind yourself a little bit. Okay, just to rearrange it, I'll leave the E on the right hand side and move the E2 to the left hand side, which is going to be the E1 minus E2 and plus E naught is equal to E. Since this is really useful, I'm going to square them all. And in order to simplify this, let me remind you the energy of a photon is equal to momentum times the speed of light is equal to Planck's constant times frequency is equal to Planck's constant times the speed of light and divided by the lambda, by the wavelength. Okay, we got so many of them. I would like to use the PC, E equals PC, since I got an equation related to P. So the E equals PC might be really useful for me. So I'm going to plug in E equals PC, plug in like P1C for E1 and P2C for E2. Okay. So the P1 is now P1 times C and minus P2 times C and plus E naught is the rest mass energy. Okay, just leave it, E naught. square equals the E square is equal to E naught square. The reason why I leave the E naught, the reason why I didn't want to expand the E naught to be E naught M naught times C square, because I'm ready to cancel the 2 E naught square, okay? So I'm gonna leave this in the original form, and the E square is equal to E naught square and plus P square times C square. Let's keep doing it. The hardest part is you are going to expand all this term, okay? Ready on the right hand side. Okay, first you're going to square the first term, which is going to be C square m times P1 square plus P2 square and minus 2 P1 P2. Okay. The next step is you square the E naught. I square the E naught, okay, and plus 2AB, right? And plus 2 times E naught and times P1 minus P2 and times C. Let's check. It's so complicated. Okay, so I can cancel the E naught squared, Okay, what is more? I can also cancel the C squared. I only get C to the first power. I cancel it, and divide all this term by the speed of light. Okay, acceptable. Is there anything else could be cancelled? Okay, let's just keep simplifying this. Write a more clearer version down below, which is the P1 square and plus P2 square, the P1 square plus P2 square minus 2 times P1 times P2 and plus 2 times E naught P1 minus P2 divided by C is equal to P square. And this P is the momentum, for the scattered electron. So I put a sub E, P sub E and P sub E. Okay, since this is the energy of the electron after the collision. Okay, we are so close. This is the equation number 2, and please observe the two equations. Please observe the two equations. Can you see how we can do the next step? Since we got the P1 square and P1 square, P2 square and P2 square. Oh yeah, I'm ready to subtract all this term from equation 1. Okay, so using 1 minus 2. Are you ready? 1 minus 2. You can cancel the P1 square, cancel the P1 square, and cancel the P2 square, cancel the P2 square. Okay, let me mark it. We got the minus 2 P1 P2 times cosine of theta. I got minus 2 P1 P2. Okay, so minus is gonna be positive. So this will be 2 times P1 P2 1 minus cosine of theta. And what is more? Oh yeah, the PE squared can be cancelled as well. So good. And minus the 2 times E naught times P1 minus P2 divided by C equals 0. Actually, I can move this term to the right hand side. But what is more, I can cancel the 2. Okay, cancel the 2. And let me remind you, what is P, the momentum? The momentum P is equal to Planck's constant divided by the wavelength. So P1 is equal to h divided by lambda 1, and P2 is equal to h divided by lambda 2. Okay, I'm ready to plug in all this with my equation, and turns out to be the numerator is the Planck's constant squared, and the denominator is lambda 1 times lambda 2 and times 1 minus cosine of theta is equal to, since the E naught is equal to m naught times c squared, so I can cancel the c, and what we are left with is the m naught times c. So it's going to be m naught times c, and times this will be the h over lambda 1 minus h over lambda 2, and is going to be the denominator is lambda 1 times lambda 2, and the numerator is the lambda 2 minus lambda 1, okay, and times the Planck's constant. Okay, keep simplifying this. We are so close. Whew. Okay, we cancel the Planck's constant. And leaves 1, the h to the first power, and this is exactly what we are looking for. This is the delta lambda. Okay, this is the delta lambda. The difference of the wavelength between the incident photon and the scattered photon is lambda 2 minus lambda 1. And we can keep cancel the lambda 1 times lambda 2. Okay, finally, the delta lambda is equal to Planck's constant divided by m naught times c, m times 1 minus cosine of theta. Whew, finally. So this is the difference of the wavelength between the incident photon and the scattered photon. And this is the angle between the incident photon and the scattered photon. This is the angle. And the m naught is the rest mass. So as you can see from this equation, the angle between the incident and the scattered photon is totally independent of the target material. It doesn't matter the target is lithium, boron, or carbon. That doesn't matter. It's totally independent of the target materials. However, the delta lambda, the wavelength difference, the difference of the wavelength only depends on the theta. And is independent of the target material. Okay? So according to this equation, the delta lambda depends on the theta between the incident and the scattered photon, and is totally independent of the target. Compton completed this experiment by using the carbon target, and he also done other experiments like using the lithium, boron, and even water. And no matter what kind of target he was changing, and the result will always remain the same. The delta lambda only depends on the theta, and the theta is the angle between the incident photon and the scattered photon. It depends on the theta significantly, and is totally independent of the target materials. Okay, so this is how we derive the delta lambda equals h divided by rest mass times the speed of light and time is 1 minus cosine of theta. Okay, hope you like it. Hope you like my version. Thanks for watching. And this is Nash.